Hey, hello, ib2 standard level students. Okay, next lesson about energy and production. Let's do some exercises. I hope you are prepared. You have pen, pencil, calculator. I don't have calculator here. Okay, here you have a calculator, your notebook, and eventually a ruler. And Tsokos, of course, today Tsokos. So open your Tsokos on page number 343. 343. Okay, and your task is, based on our last lesson, do two exercises: exercise number 11 and exercise number 12. Okay, so you can obtain 4, 7, 9, 11, 13, 15, 17, and here 18, 20, 25. You have 45 minutes, okay, to solve these two exercises. The best will be working alone. If not, like Franco, Maciek, you are doing exercise together always. You can communicate now, and you have 45 minutes. Stop video for 45 minutes. In 45 minutes, I'm going to give you solutions for this exercise, and your task will be to check, compare your solutions with my solutions. I hope mine will be correct, and of course your will be correct, and then try to assess. You have number of points, try to distribute these points into your work. Is it clear? So start your 45 minutes. Okay, 45 minutes later. Yeah, 45 minutes later. Okay, so let's do exercise number 11. I have a text here, will be a little bit easier to me. I don't need this. Unfortunately, I don't have calculator, so I will be working without calculator, and eventually I will turn calculator, the built-in calculator. Okay, exercise number 11A1, nuclear power plant, 800 megawatts, efficiency 0.32, fission is nuclear fission reaction is given. We have to prove that energy released in one fission reaction is 180 megaelectronvolts. So this is something like revision of our nuclear energy topic. We have equation, reaction, left part, right part. You have to find mass of the left, which is 1 neutron plus 1 uranium. Masses are given here. This is neutron, this is uranium, so this is 1.009 plus 235.044. In units it is 236.053 units. Mass right hand, we have xenon, strontium, and 2 more neutrons, so we have 139.922 plus 93.911, and 2 neutrons, 2 times this is 2.018, which add together is 139.922 plus 93.915 plus 2.018, which gives 235,855. 235,855 of units. Mass defect difference between left and right is 236.053 minus 235.855, which gives 198 of units. I'm going to write this here, probably it will be needed later, so mass defect is 0.198 of units. Okay, and if you want to convert it into mega electronvolts, you have to multiply this by 931.5, which approximately gives us 180 mega electronvolts. Okay, so this is AI. Now AII. Second, estimate the specific energy of uranium. Specific energy of uranium is the amount of energy which can be released from 1 kilogram of uranium. So let's look. We know that energy which is released from 1 uranium is 180 mega electron volts. So first convert this into joules. So 1 mega electron volt is 1.6 times 10 to the power of minus 13 of joules. So we have to multiply 180 times 1.6, which gives 288 times 10 to the power of minus 13 of joules. This is energy released in one reaction. I'm going to write this somewhere. Probably it will be needed later. E1, it will be energy released in one reaction as 2.88 times 10 to the power of minus is minus 13, so minus 11 of joules. This is energy released in one reaction. And we have to know also a mass of uranium in kilograms. So mass of uranium is given in units, is 235.044 in units, and to convert it into kilograms you have to multiply it by mass of 1 unit in kilograms, so which is 1.661 times 10 to the power of minus 27. Yes, I remember this number. And multiply 235.044 times 1.661, which gives 390 times 10 to the power of minus 27 kilograms, or 3.9 times 10 to the power of minus 25 of kilograms. And I'm going to write this somewhere. So mass of 1 uranium is in kilograms 3.9 times 10 to the power of minus 25 of kilograms. I think that it will be necessary later. Okay, so let's finish the second. Specific energy. As I said, specific energy is mass of 1 kilogram. We can use simple proportion. We know that mass of 1 uranium, so 3.9 times 10 to the power of minus 25 kilograms, releases energy which is equal to 2.88 times 10 to the power of minus 11 joules. And we have to find energy which is released by 1 kilogram of uranium. So we have to divide this by this. So energy released by 1 kilogram of uranium is 2.88 times 10 to the power of minus 11 divided by 3.9 times 10 to the power of minus 25. And if I didn't do mistake in my writing or calculations, the result is 0.738 times 10 to the power of, we have minus 11 plus 25, which gives 14, 10 to the power of 14, or 7.38 times 10 to the power of, and this is, we have bigger numbers or smaller, so this is 10 to the power of 13 of joules per kilogram. So specific energy is amount of joules which can be obtained from 1 kilogram, and I've obtained 7.38 times 10 to the power of 13 joules per kilogram. Okay, so write this somewhere. So this specific energy is 7.38 times 10 to the power of 13 joules per kilogram. Of course, there's probability that I've made a mistake, so sorry for this. I hope not. Okay, and now show that the mass of uranium undergoing fission in 1 year is about 1,500 kilograms. So this is challenging, but not to you, I hope. Okay, so let's look. Now we have to use this efficiency. We know that this reactor produces 800 mega electron volts of energy, of power, with efficiency of 0.32. I wrote 0.38, 0.32, of course. So we have 800 MeV with efficiency of 0.32. So what is a power taken from uranium? Okay, so we have to multiply 0.32 times this power to obtain 800 megawatts, because this, this is megawatt, of course, megawatts of power. So power taken from uranium is 800 divided by 0.32, so probably 2,500. Yes, exactly, 2,500 megawatts. What does it mean? It means that the energy extracted from uranium is 2.5 times 10 to the power of 9 joules per second. Okay? In 1 second, energy obtained from uranium is 2.5 times 10 to the power of 9 joules. Okay, the question is about energy per year. So let's find how much energy must be obtained from uranium per year. So we have to multiply this 2.5 times 10 to the power of 9 joules per second times number of seconds in 1 year, which is 3.15 times 10 to the power of 7. Again, I remember this number. So 2.5 times 3.15 gives 7.88. 7.88 times 10 to the power of 16 joules per 1 year. This is the amount of energy which must be obtained from this from the uranium. The question is how many what is the mass of uranium which must be undergoing fission in 1 year. So we know that this is amount of energy which is released. Yes? And let's look. We have also specific energy of uranium. So amount of energy which can be released, which is released from 1 kilogram. Yes? So if 1 kilogram of uranium gives us 7.38 times 10 to the power of 13 joules of energy, okay, so what mass is needed to obtain 7.88 times 10 to the power of 16 joules in 1 year? And I see that I will not obtain 1,500. I don't know why, because we have to finally multiply this by this. So our final answer is 7.88 times 10 to the power of 16 divided by 7.38 times 10 to the power of 13, which is a little bit more than 1,000, but it's not, definitely not 1,500. So there is a mistake in calculations. I've obtained 1,070 kilograms. The result should be 1,500. Let me check one by one, but I don't know I'm able to find mistake without calculator. If not, so sorry, maybe you will be able, but let me check. We have to check second and we have to check third, because I'm not sure that this energy, specific energy of uranium is correct. Okay, we know that this is energy which is obtained from one reaction, 288. Okay, this looks good. This is correct. Okay, mass of uranium 1661 times 10 to the power of minus 27, 390 times to the power of 3.9 times 10 to the power of 25. It looks correct. And again, one uranium atom, so mass 3.9 times 10 to the power of minus 25, releases this amount of energy, 288 times 10 to the power of minus 11, 288 times 10 to the power of minus 11, yes, looks good. So how many 1 kilogram? So we have to divide 288 by 3.9, so let me check it again, 2.88 divided by 3.9 is 738. Okay, so 7.38 times 10 to the power. Okay, so this is specific energy. 7.38 times 10 to the power of minus 13 joules per kilogram. Okay, and now 800 megawatts and efficiency of 0.32. nuclear power plant produces 800 megawatts. Okay, so power input is this divided by this, so 2.5, so 2.5 times 10 to the power of 9 joules per second. Okay, and now we have to multiply this by number of seconds in year, so 365 times 24 times 3600, which gives 3.15 times 10 to the power of 7. I have 3.15 times 10 to the power of 7, and 2.5 times 3.15 gives 788 times 10 to the power of 16. Yes, and 1 kilogram releases 7.38 and x kilograms releases 7.88. I've checked without calculator and still I have a result 1770 kilograms except 1500 kilograms. Maybe mistake in this answer, or I have somewhere mistake in my calculations. But okay, your task is to check, to calculate again. If you will find mistake, please inform me. Then I give you a plus, of course, a plus. Okay, don't waste the time. Let's do B. I think method is correct. Method must be correct. So try to find mistake or assume that this is a wrong answer. Okay. So B. A nuclear fission reactor describe the role in a nuclear fission reactor. Describe a role of moderator. Okay. So what is a moderator? The main function of moderator is to slow down fast-moving neutrons to make further fission reactions possible. Okay. Second, the control rods are movable rods which can be introduced or removed from the reactor and to absorb neutrons to control the rate of reactor. Okay, and heat exchanger is a kind of device, yes, which exchanges heat between the cooler, which cools down core of the reactor, and ordinary water, which is converted into the steam. So this is something which which converts heat from the liquid which cools down reactor to liquid which goes outside the reactor and it's converted into steam. Okay, next, suggest what might happen to a nuclear fission reactor that does not have a moderator. Okay, so moderator is something which slows down fast-moving neutrons. So if moderator doesn't exist, the neutrons are not slowed down and further reactions cannot be possible because, as you know, a neutron to initiate further reaction must have a speed from a given range. It cannot be too slow, it cannot be too fast. If it's too fast, then further reactions are not possible. It cannot initiate, the chain reaction will be stopped and reactor will be colder and colder and colder, and the amount of energy produced by the reactor will be less, less and less. And last, state one advantage and one disadvantage of nuclear power plants. So the biggest advantage, no CO2, which is a greenhouse gas. Yes? And disadvantage, in my opinion, the biggest disadvantage, nuclear waste. We cannot proceed it. Currently, nuclear waste can be only stored. Okay? So are toxic, are radioactive, which can be stored. Okay, and how this exercise? I hope correct. So let's do the second exercise, exercise number 12, about pumped storage system. I'm going to do this in the same way. I hope that now there will be not mistakes in text and eventually not mistakes in my calculations. Okay, so pumped storage system. In a pumped storage system, the high reservoir of water has area of 4.8 times 10 to the power of 4 and average depth of 38. When water from this reservoir falls to the lower reservoir, the center of mass of the water is lowered by a vertical distance of 2 to 5 meters. The water flows through a turbine connected to a generator at the rate of 350 meters cubed per second. calculate the mass of water in the upper reservoir. Okay, mass of water is, I hope that you remember, is density times volume. Okay, density of water, if it's not given, then is 1000 kilograms per meter cubed. So you have to find mass by multiplying surface area times average depth times density in kilograms per meter cubed. So we have 4.8 times 38. Okay, which is 182, approximately 182 times 10 to the power of 4, and this 3 is 7, so 1.82 times 10 to the power of 9 of kilograms. So this is mass of water. Let's write this here, 182 times 10 to the power of 9 in standard units, so kilograms. Second, determine the loss of gravitational potential energy when the upper reservoir has been completely emptied. Okay, so it's also not difficult. Gravitational potential energy is related with mass times gravitational acceleration times height from which this mass falls. So in this case we have 182 times 10 to the power of 9 times 9.81 gravitational acceleration, and height from which it travels is 225 meters. We don't need to add or subtract 58 because this is written that the center of mass is lowered by. Okay, so center of mass is displaced by 225 meters, so multiplying 1.82 times 9.81 times 225, I have 4017 times 10 to the power of 9, or 4.02 in 3 significant digits times 10 to the power of 123, so 12 of joules. This is the amount of energy which is lost by falling water from 225 meters. So let's write this here, 4.02 times 10 to the power of 12 of joules. Okay, estimate the power supplied by the falling water. So let's look. We have information that in each second amount of water which falls is 350 meters cubed. Okay, so we can calculate what is the energy given in each second. Yeah, so let's look. Potential energy in 1 second is related with falling of 350 meters cubed of water in 1 second. Mass of this, let's name it mass 1, mass in 1 second, is of course 350,000 of kilograms, because volume is 350 meters cubed and density is 1000 kilograms per meter cubed. So mass of water which falls in 1 second in this system is 350,000 of kilograms. Of course, this mass must be multiplied by 9.81 and multiplied by height from which it falls, so 225, which results in 350 times 9.81 times 225, and remember times 10 to the power of 3, so 773,000 times 10 to the power of 3, which gives 7.73 times 10 to the power of 678, 10 to the power of 8 of joules. Okay, so you can obtain the same result by dividing this total energy by fraction of this over this. Yes, so if we know that 350 meters cubed is the part of the volume which falls in 1 second, and we know total volume of water, then we can take the same amount, the same part of energy to calculate the amount of joules in 1 second. The question was about power, so power is energy over time. If this is per 1 second, then power of course is 7.73 times 10 to the power of 8 of watts. Okay, so I'm going to write this here, 7.73 times 10 to the power of 8 of watts. Okay, and the last but the longest, this. The efficiency of the plant in converting this energy into electricity is 60%. The price of electricity sold by this power station at peak times is 0.12 per kilowatt hour, and the plant can buy off peak electrical power at 0.07 per kilowatt hour. The efficiency at which water can be pumped back up the high reservoir is 0.64%. Estimate the profit made by the power plant for a single emptying and refilling of the high reservoir. Okay, so let's look. We can the plant can buy off peak electrical power at 0.07 per kilowatt hours, and the efficiency at which the water can be pumped back to high reservoir is 0.64. Okay, so let's calculate what is the total cost of electricity if this high reservoir is emptied. Okay, so in D. So let's look. We know that the efficiency is 0.60. Okay, so efficiency is 0.60 and the amount of joules is 4.02 times 10 to the power of 12. Okay, so we have to find what is the amount of electricity produced. Okay, it will be total energy times 0.6. So 4.02 times 0.6 gives us 2.41. 2.41 times 10 to the power of 12 of joules of energy, of electrical energy which is produced when water falls, electricity. Okay, if we have to convert this into kilowatt hours. Okay, I hope that you remember that 1 kilowatt hour is 3.6 times 10 to the power of 6 of joules of energy. Kilo is 1000, watt is watt, and hour is 3600. 1000 times 3600 gives 3.6 times 10 to the power of 6. And we don't know number of kilowatt hours, but we know that total energy is 2.41 times 10 to the power of 12 of joules. So this times this equals this times this. So we have to divide 2.41 by 3.6. Okay, which is 2.41 divided by 3.6 is 67, 0.67 times 10 to the power of 6 of kilowatt hours, or 6.7 times 10 to the power of 5 kilowatt hours. And we know that 1 kilowatt hour is 0.12, okay, of cents. So 1 kilowatt hour, the cost is 0.12 American dollars, not cents but American dollars. And we know that in emptying of a higher reservoir we have 6.7 times 10 to the power of 5 of kilowatt hours. So we can calculate cost. Let's use maybe C like cost. And C is this times this over this times this. So we have to multiply 6.7 times 0.12, obtaining 0.80 times 10 to the power of 5 of dollars, which is 8.0 times 10 to the power of 4 of American dollars. Okay, so this is the cost of electricity if higher reservoir is emptied. And now we have to do the same. Let me read again. The price of electricity sold by this power station at peak times is 0.12, and the plant can buy off peak electrical power at 0.07, and the efficiency at which water can be pumped back up to the high reservoir is 0.64. So how to do this? We have cost of electricity which is sold to the customers. Water falls, releases energy, and energy is converted into electricity. And the cost of this electricity is $80,000. Okay, and now the power plant operator can buy back the electricity for 0.07 per kilowatt hour and pumping this to high reservoir with efficiency of 0.64. So now we have the same water, which must be pumped, the same amount of water, which must be pumped up, but with efficiency of 0.64. So now we have this, we have to calculate amount of electricity which is needed to pump it back. Okay, so we have to do the same calculations but in opposite way. We have total amount of water which is pumped up for a height of 225 meters, so 4.02 times 10 to the power of 12 joules of energy is needed, with efficiency of 0.64, which gives 4.02 times 0.64, which is 2.57. 2.57 times 10 to the power of 12 joules of energy is needed. Yes, wait, we have to pump this amount of water. Oh, probably I've calculated in a wrong way, because again, this is total. Let me back here. This is total energy which is released by water, and efficiency is 0.6. So amount of electricity which is obtained is this. Okay, so this is correct. But here we have to pump up with efficiency of 0.64 the same amount of water. So now let's look. We need more energy to pump it up. So let's look. We have 0.64, sorry, I'm crossing this. We have 0.64 efficiency of the system. Yes, and we have to pump up the 4.8 this amount of water, 1.82 times 10 to the power of 9 kilograms of water. Yes, with efficiency of 0.64. So how much energy is needed? We have mass times gravitational acceleration times height, which is, we've calculated this, 4.02 times 10 to the power of 12. Yes, so this is amount of energy, but now we know that amount of energy to pump it back is much more bigger, because to obtain this we have to use energy with efficiency of 0.64%. So finally amount of electricity needed to pump it up is 4.02 divided by 0.64, which is 6.28 or 6.28 times 10 to the power of 12 of joules. Sorry, this is correct. Yes. So this energy is needed to pump it back. Okay. And now, how many kilowatt hours is it? Again, the same proportion. 1 kilowatt hour is 3.6 times 10 to the power of 6 of joules. And how many kilowatt hours is 6.28 times 10 to the power of 12 of joules? Simple proportion, multiplied and divide 6.28 divided by 3.6. gives 1.74 times 10 to the power of 6 of kilowatt hours. So this is amount of energy needed to pump it up. Okay, and now cost. Cost to pump up, so C up is 1.74 times 10 to the power of 6 times $0.07 per 1, which gives us 0.12 times 10 to the power of 6. Yes, 0.12 times 10 to the power of 6, which gives 1.2 times 10 to the power of 5 of American dollars. So let's look. If system is emptied, yes, then the energy, the cost is $80,000. Okay, this is cost of electricity which is sold by this by the operator of this system. But if system is refilled back, the cost to do this is $120,000. Okay? So what is the profit? Minus $40,000. So less energy is less money is obtained by refilling than if it's again buy from the customers. Okay, I hope that the solutions are presented in the correct way. I hope in your solutions are also correct. Please check your calculations compared with mine. If you have some questions, some parts which must be discussed, inform me by in the comments of the movie or in the classroom. Okay, see you next time. Bye.